look at increasing the high voltage on the photomultiplier tube. We start with the signal from the pulsar, the test output of the pulsar going to channel 2. We see 2 pulses from the LED about 1 microsecond apart, and we have some additional things connected in the photomultiplier. So we have the 2 connectors of this voltmeter that are connected to a high voltage monitor. So if we multiply by 100 the value displayed here, we get the high voltage that is applied to the photomultiplier. This is the minimum value, so it doesn't go to 0 but stays there. It's equivalent to 0. And then we take the output of the photomultiplier and we are going to connect that to a channel 1, the yellow trace in the scope, and we'll adjust the high voltage with this knob and see what happens, what kind of signals do we see from the photomultiplier that will be collecting the light produced by the LED. And maybe we can catch some muon, but likely we'll only see the response to the test pulses. So I'll start increasing slowly. So now I'm in setting 2. We see minus 2.8. This should be equivalent to 280 volts of bias in the photomultiplier. Now we are close to 500, about half of what you would see. And maybe you can start seeing a little bump appearing in the yellow signal. For reference, the scale is 100 millivolts from the base to this cursor line. So we go to 700 volts. Now it's clear for the second. Notice that somehow the second pulse produces a bigger signal than the first one. Not sure why. This is 800 volts. This is 1,100, minus 1,100 volts in the photomultiplier. First, I'm going to zoom in the first pulse from the LED. And now I'm going to switch the pulsar off. So you see, with the LED light, we get a signal of about 550 millivolts. When I switch the pulsar off, it disappears. But if I change the trigger to a lower value, we start seeing other signals that come at a relatively small rate, a few per seconds, but they are quite smaller than what we had before. We can make the display persist for some time and we catch a few. So these are now signals from real events that are within 100 to 300 millivolts. I want to trigger in the low falling edge, get a nicer distribution. So these are the things we really want to catch to detect muons, either when they are stopped in the detector or when they decay. So now we are triggering at 4.8 millivolts below the base. So if we have a signal below that, the scope triggers. And we can see here the frequency of triggers. So this is now oscillating around 100 hertz, more or less. That means that we have a 100 times per second we see a signal that goes below, a pulse that goes below 5 millivolts. And if we vary this, for example, now we are at 20 millivolts, and the frequency went down probably around 30. And if we keep doing that, we can see clearly that the frequency of triggers depends. So it's less. Now we are at 40 millivolts. Of course, a much smaller number of cases where we have a large enough pulse that goes below 10 millivolts. So this will appear as another measurement in the Excel file. Channel 1, the yellow trace, is the output of the amplifier. And channel 2, the blue, comes from the PMT. We split the PMT in two. And note we have a 780 volts, relatively low. So these are signals from the LED pulsar, and I want to show how the amplifier saturates. So as I increase the as I increase the high voltage, the amplitude of the signals increases. If I reduce it goes down, both from the blue, which is the signal from the PMT, and the output of the amplifier. But after some point, the amplifier doesn't increase anymore. It saturates, and I keep increasing the signal from the PMT. There is a maximum output for the amplifier, which is, I believe, reached only in the case of signal from the LED pulsar. Probably we wouldn't see that in signals coming from the real muons.